This talk, Advanced SQL with SQLAlchemy, I'm going to jump ahead just to this slide in case you wanted to grab some code or this presentation and play along. Probably not the best ordering there, but. So I'm Ryan Kelly, CTO of Capital RX. We are a venture-backed startup here in New York City. We are a pharmacy benefits manager. We are hiring. That is our website. You can find more about what we do. And we'll just get going. So we'll kind of cover topics in roughly this order, really how I think about SQLAlchemy, or SQL, and then why SQLAlchemy and Postgres in particular. We'll talk a little bit about then 4 SQL features that I really love. So SQL, first and foremost, is a declarative language. And what does that mean? It's like when you treat your infrastructure as code, when you say, I want something to look like this, right, you're really doing the same thing in SQL. You are declaring that you want a result, an output that assumes this kind of structure, this shape. So if you want a sum, an aggregate, something like that, right, you are declaring that you want this aggregated. You don't need to necessarily look at the data or potentially know anything about the data beyond the name of anything. SQL, for me, and I work in healthcare and we generate and consume a rather large amount of data, has always been the right choice. Unless you are Google or Facebook, which you're probably not. SQL databases like Postgres function perfectly fine up until, petabyte range, and people are running Postgres clusters at that scale. And why is that so great? Well, in Python, we have this really awesome library, SQLAlchemy. I've been using SQLAlchemy probably for 9 years now, and I've programmed in many other different languages professionally. SQLAlchemy is the most amazing library in any language. I mean, React really gives it a run for its money. Really love React, but SQLAlchemy really has a lot of features that make accessing and utilizing the full power of your SQL database really, really simple and really similar to how you would actually do it when using real SQL. Why Postgres? I've been using Postgres for well over a decade. It's fast, it's scalable, it's open source. There are great hosted options, available on AWS and some of the other cloud providers as well. SQLAlchemy obviously has great support for it, and many of the optional features that exist in Postgres are available in SQLAlchemy. PsychoPG, another great library, actively maintained as well. So kind of the first thing, this is what really got me hooked on Postgres as a database, and that was types and operators. It was kind of the thing that really clicked for me is about 9 years ago, I discovered that Postgres had this feature called arrays. And you could store lists of data in a single column. But not only that, you could take advantage of Postgres operator and indexing systems to really let you filter and explore and expand and use that data in ways that really didn't occur to me and were not available in any of the traditional SQL systems. At my previous company, we implemented a system of tagging records by placing tags on those individual records in arrays. And then you could create a GIN or a GIST index on that array column to filter the data. And this allowed us to look at millions and millions and millions of rows of data and filter on an array column almost instantaneously. At one point, that system probably managed about 500 million pharmacy claims. And you could literally filter down to one record in a couple of milliseconds. So that was a really powerful feature to categorize and organize our data. And you can see here some of my favorite features that are made available by Postgres types. Tagging, just discussed. Time binding, right? You can use interval types. Postgres has this interval types, and we'll go into that. Interval types allow you to filter on a specific range of things. Advanced constraints, exclusion constraints. So say you want to have a set of time series data, and you want to assert that none of this data overlaps in time. You can actually write a constraint in Postgres natively that will perform that for you. And the last thing, which a lot of people really love today, is JSON. You actually have full access to JSON, validated JSON, JSON operators, and being able to filter and query and index JSON documents inside of your database. So it's a really more flexible solution. So when you want the power of a SQL database, of structured data, of relational data, you can use it, or you can just insert JSON documents into your table and use them that way instead of having to go with a document database. This is kind of the first example, and it goes back into how we approach tagging. You can see here that some generic record object, and we just have some tags on it. Maybe this is like tickets in your ticketing system or something. Add these all to the database, and then you can see here, right, this AND operator. And that's saying, do these two arrays overlap? Do they have anything in common? So you can actually treat these arrays as if they were sets. And there are many other operators. You can actually put @ greater than to say, does this array contain that one, or vice versa, does it contain it in the other direction? And these kinds of queries, right, are not something that's very simple and straightforward to organize or do in a traditional SQL fashion, right? You'd have to have a separate table with tags, with a foreign key that relates back to this table. You'd have to filter on that other table using exists and probably a group by, and then join those two tables together to get that result set. Whereas here, you can put that data right on that column, right? Just right there as part of that record, and then you can filter on it very simply and very efficiently, especially if you have an index created on it. And this is the output from that query. So you can see here, right, we've got defect and backend, and it's these two. And then, right, that's what comes out when you run that code. This in particular is actually, if you play around with the examples, it'll actually print these things out as you run it. You can change anything you want here. You could very simply change to filter on whatever else you want or add more data and play around with the operators. I definitely encourage you to go into the documentation of Postgres. But I do want to point out here, right, you could just use .op. Any operator, and there are dozens and dozens of custom operators in Postgres, are all available just by calling .op in SQLAlchemy. SQLAlchemy makes it really simple to access all of these underlying features. It also, you can actually, if you look in the examples as well, you can declare these array columns, right? There's support in here for actually creating these array columns as part of your schema. Here's another example of using tags. Say you wanted to know how many tags were on a particular record, right? Another really great thing about SQLAlchemy is func. Func is magic, right? Any attribute you call on it will be rendered into a function of that name. There are some special cases where certain functions like count are actually going to be rendered as count star, or where something like current date is actually a function but is not called with parentheses in SQL. And SQLAlchemy will handle those cases for you, but it gives you full access to custom functions in the database. And you can even define your own functions and call them just in this same way. If you put your function in a schema, it's a little bit trickier to call it, but you can still get at it with func. Func.unNest is a function that takes an array as an argument and turns it into a table. So this is actually a projection. So every single tag will now become a new row in a table, and then you can perform your standard SQL group by and order by functionality on it. And this is the result of that, right? We saw in our data that we had 2 records that were tagged backend, 2 records that were tagged defect, right? Enhancement front end, so on and so forth. And it works just like any other query. But you can now turn an array of data that's kind of horizontal on this row and turn it into a projection of rows. And you can do this with even more complicated data types. You could actually do something really crazy, like have an array of JSON documents in this thing and actually unnest it in the same way. There are functions to do that as well. But really here, SQLAlchemy is not limiting you, right? It's not preventing you from doing anything. It's really enabling you to create and define and call and use whatever functions you want. The other thing, as another feature to point out here, right? group by, and order by, right? Using this literal one, literal two syntax, you can actually specify by position in the query. This is one, and this is two, about how to group by and order by. That's a Postgres feature. Some other databases support that as well. But this is another way, right, that SQLAlchemy is just letting you write SQL as you kind of wanted to write that SQL. Common table expressions. This was another really cool feature that I adopted fairly early on when it came out. And I'm really happy to report that SQLAlchemy supports them fantastically, as well as recursive CTEs, but I would not recommend using those. SQL's ability to be abstracted, right, is pretty limited. If any of you have ever written direct SQL queries, right, you'll notice that you're repeating a lot of the same logic over and over and over again. You could put some of it in functions, right, but that has a performance impact, and some of the calculations that you're performing really can't be optimized that way. So there's a feature called a common table expression, which allows you to really just take a chunk of a query and treat it as if it was a table. You could do the same thing with a subquery, but the nice thing about common table expressions is you can actually reference them multiple times. So if you wanted to join a common table expression to itself, or join it multiple times with different join clauses, right, that's an option to you. And the way that I normally use these is I'll write a CTE, I'll write another one, another one, another one, and there'll be a whole stack of CTEs at the top of my query, and then finally, just at the end, something that executes those CTEs and pulls the results together. And this makes it much, much easier to read a SQL query. If you write a SQL query and do the same thing and you inline all of those statements, right, it's almost impossible to read or follow the logic, and everything is duplicated all over the place. Incremental query development is probably the best way to describe it. Is I'll write this CTE, look at the output, write another CTE that filters it down, modifies it, write another CTE that does some more work to it, and then finally at the end, output the final result. CTEs in Postgres, up until the latest version, were actually a total optimization fence. So they would be executed once and the results stored. Today, there's actually some support for inlining them. So they can actually function just like a subquery in terms of performance. So what we're going to look at here, right, is we're just going to make up some fake sales. So we're just going to create 1,000 fake sales in our systems. And then just perform some basic calculations on them. So here, right, we're going to calculate what are our sales by region, okay? You can see here that we've got this concept of a store ID. The store ID is actually a structured identifier, and the first 4 characters of it are going to be a region. If you look at the code provided with this, it's going to be a lot clearer, but first 4 characters are going to be the region, right, and then the amount. And so what kind of benefit does this give us, right? When we do this, right, we make this .cte call, right? This turns this expression essentially into a table. Just like any other SQLAlchemy core selectable table object, this is actually now like a table. You can treat it like a table. You can do all the table things. You can access columns with .c and do all of those different things that you want to do. And here you can see that we're performing some calculations. Now these aren't particularly expensive calculations, they're just kind of an example, but these are the sorts of things that putting your code in a CTE will help optimize. So if you need to make some really expensive function calls in here, say func.sum actually took 1,000 times longer than it does, right? It may make sense to actually put this in a CTE so it only executes once, and then you can reference that result in many other places. Here you can see these are the store IDs I was talking about. It's just a region, a state, and just a random number following it. And here you can see sales by state, right? Sales by store. Again, nothing too crazy here. CTEs and some of the other functionality that we talked about. And then you can generate this sales report, right? You can see how you can actually treat those queries that you wrote and compose them together as if they were tables that you had defined in your database. So standard notation, right, .c to access a column on your table. You can label them whatever you want, and you can perform, you know, any other labeling, and you can then join these things together, right? You're just treating these things as if they were regular tables. Order by is there. You could also put you could put more expressions in. You could put sum and other aggregates. You could put any other function calls that you wanted inside of this query. And then you could turn this query into a CTE And then you could make that query be used in another CTE and so on and so forth. I actually had one project that admittedly got kind of out of hand, and it would generate the compiled SQL output from that query in maybe 2,000 lines of Python that was a 25 megabyte query, 25 megabytes of data in just a query, and Postgres would actually execute it, rather comfortably. But this really allows you to compose your data and your approach to things, whereas in regular SQL, there's not any other way to do this. And SQLAlchemy just, it's just like using anything else in SQLAlchemy. There's no special syntax or function calls or notation, right? It's just as if you had defined this as a regular table that you can select from and just used it in your query. Output from this, relatively straightforward. You can see that we're actually joining those 3 CTEs together and then ordering them. And it's, should be pretty straightforward. Another really, really cool feature, window functions. Window functions allow you to look around the row that you're processing or at other rows in that query. So if you want to find the next row, you can use the window function lead. And you don't have to look 1 row ahead. You can look 2 or 3 or however many rows that you want. Lag can look behind that row. You can order these with a window, what's called a window clause, right? And you can look inside of specific cuts of the data. So say we have, store ID, right, or region, whatever, and we want to look at just everything in that region, right? Window functions would allow us to write a query that on that single row also looks at that entire region. Normally, the approach to this would be taking some CTEs maybe and computing some results first and then joining the query back together. Whereas with a window function, you can actually do that directly and in one statement. You can use window functions to calculate a running total. So in your current query, right, as you've ordered the rows, you can actually sum up and find a running total of values. You can add aggregates to each row, like I just mentioned. You can peek at the next and previous, and you can find quite efficiently the latest record. So say you have a series of transactions that occurred, sales, right? And you want to find the latest sale for each store. Window functions make that really easy. Whereas if you don't know the actual date of that sale or some other way to order it, right? Like how do you filter on that condition? Window functions allow you to generate a row number to figure that out relatively quickly. So as I was just mentioning, right, finding the latest sale. Right? The row number function will add a number, increasing 1, 2, 3, 4, 5, 6, based on whatever order and whatever partition you specify. So if I want to find something specific to store, right, we look at this partition. And if I want to find something specific, and if I want to order by the latest sale, the most recently occurring sale, right, then I just sort by date descending. And you can see here, right, here's func again. Right, and we're just calling row number. And then SQLAlchemy has support for over. And you can literally call over on any function. SQLAlchemy doesn't really have any special behavior or any special knowledge about functions you can call over on, and you can pass them into the database. Your database may complain if your function is not actually an aggregate or something that supports a window. But it's really easy. And you can specify a list here instead of just a single item to partition on multiple columns. Same thing with the order by. And so you can label this as your row number, right? And again, find the latest sale. So what this is going to do is it's going to label the latest sale with the row number 1. And so when we go to use that in this subquery, right, we join this together to sales, this will actually filter to the latest sale. This will give you the very latest sale for that store, actually for all the stores. And there's nothing really special here. Here we're using a subquery, right? Works the same way, just like a CTE. Some different performance implications associated with it. But again, just a regular standard join, IDs, row number 1, and this will actually give you the latest sale. There's some random names in there. Cat selfie duct tape, actually a real product. I was at the store, they were actually selling cat selfie duct tape, and I don't know why. But again, right, you can see here, store IDs. This is the whole list of store IDs, and obviously they're unique, but this is the latest sale that was randomly generated for each one of those stores. I use this very frequently. So when we get when we get data that comes in, right, if I want to look at the latest claim for someone, this is a fine use case, but prices update rather frequently, and if I want to know what the latest price for any product is, I write a query like this all the time. I use this kind of query, and this type of query is all over our code base. Like, I probably use something like this a dozen times a week, just when I'm looking at data. Here is our sales report again, and this is kind of another way to approach the sales report, right? As I mentioned before, you can compute aggregates almost directly on a row without the need to join to anything. So here, right, if we want to partition by the first 4 of the store ID, which is the region, right, we can actually calculate the sum of this column for this partition, but without actually having to perform an aggregate and then join it together, because we're also doing these things, right? We're going to get the sales by state, right, and then we can also have sales for store. And again, same kind of output. So there's actually a couple different ways to skin this cat, but window functions are definitely a useful thing to have in your pocket, and it's really great that SQLAlchemy makes them just so simple and so seamless to use. Kind of the last, I guess, major feature that I want to talk about is grouping sets. So as we saw in some of my previous examples, right, we had group by, right? That's how we aggregate. That's how we say we want to split the data by these chunks. Well, what if you want to split the data by these chunks and those chunks and that chunk and this other chunk and these different chunks of data, right? If you want to do this in one query, right, without grouping sets, it's not possible. You would have to run multiple queries, or you'd have to union multiple queries together, right? Say you have a sales report. Really common ask here is I want data aggregated by region, but I also want a total row down at the bottom, right? Grouping sets allows you to do that in a single query, in a single output, right? One single pass over the data. Instead of needing to compute some sum over multiple different passes of the data, right? The grouping set will actually allow you to achieve that more efficiently. So I would say probably just about the only use here for me is actually in reporting, but it is a very handy thing to know. So here, SQLAlchemy actually gives you access to grouping sets with this func, with func, right? So you can actually say, I want a query that's actually grouping by the region and the state and the store ID all at once, right? So we're going to calculate this aggregate for these different areas, right, all in a single query. So when that executes, right, this is actually, the first time I did this, I was like, this output doesn't make any sense. What are all these nulls doing? What are all of these empty columns? What is all of this blank and missing data, right? But this is actually what grouping sets is doing. And if we were to go back and look at some of our previous examples, you would see that these numbers, sales for store, right, or sales for, for the region, right, they all match, right, that other query. And you could actually pull this data, right, in one single pass, and you would probably have some other system that pretties it up and puts it into a nicer format, right? But it's a way to get these different aggregates without critically having to change the structure of this, right? You want region, state, store, and a sales amount, right? You don't have to change the structure of this upper query. You can actually use grouping sets to compute it at different levels all at once. And for me, when you have a lot of data to process, like even just iterating over a query, doing a development on a query, right? Even if it's taking 20 seconds, 30 seconds to run, right? Every single time I change it, I run it to see what that change did, right? Then you're going to do it for these other aggregates. It saves you a meaningful amount of time, even when you're doing development. And then when it goes to production, and there's a much larger data set, it runs much more quickly. Users will want to run a report. They might want to change some filter on it, run that report again. And if anything is taking too long, users are going to come to me and be like, well, why is this query taking so long? And I definitely don't like when users complain. Here's another example of a different kind of grouping set. So before, we had just regular grouping sets. That allows you to specify exactly what grouping columns you want, whereas you can use something like rollup to actually calculate the grouping for the combination of those things. So it would be essentially, I don't like this presenter, 3 of these, right? 2 of these, and 1 of these. Nope, let's go back. And so you can see that it's actually grouping by 1 of these, right? 1 of these, 1 of these. And here, 2 of these, right? 2 of these, 2 of these. And then all 3, all at once. So that's another way to efficiently calculate and compute and write aggregates at different levels. And in the code that's provided, there may even be an example with cube. Cube is another one that says, for every single combination of these different groups that you've specified, calculate these aggregates and run this query. That one I find that I less frequently use, and I didn't include an example of it here, but it may be something that you might find useful in your own business. And that's it. That's the end. Thank you.